Hi everyone, let's continue. So what happened when the gradient vector equals 0? Okay, so point where the gradient vector is 0 will be called critical point. At critical points, the property that we have just discussed do not apply. Okay, at the critical point, we will have any one of the following possibilities. We might have local maximum, local minimum, or saddle point. So saddle point means it's neither max nor min, but the gradient vector equals 0. Okay, so we will talk about more details for these cases in session 12.8. Okay, now let's look at the gradient in the space. So what we have been doing, we have z is a function of x and y, and then the gradient vector is in the xy plane. Okay, now we can consider w is a function of x, y, z. Okay, so for a 3 variable function, so let's say w equals let me see. Okay, f of x, y, z. Okay, so this is the 3 variable functions. We have 3 independent variable, and the output is a dependent variable w. Okay, then we can also define this gradient vector b. So we have 3 coordinates: partial f, partial x, partial f, partial y, and partial f, partial z. Then notice that f is a function from R2 to R. Then the gradient is a vector value function from R3 to R3. Okay. So, and keep in mind that z equals f of xy. This is just like the level curve. Okay, this is just like the level curve, level set of the function f of xy. Z, let's say we can use f of xy minus z, and or z minus that. Okay, maybe it's better to use z minus that. So z minus f of xy, and the level set of this capital F equals 0. Okay. Then next formula for the tangent plane is we let f be a differentiable function at the point ABC if the gradient vector is not 0. Then the tangent plane is partial f, partial x, evaluates at ABC times x minus a plus partial f, partial y, evaluate at ABC times y minus b plus partial f, partial z, evaluate at ABC times z minus c. Why is that? Okay, do you remember that so if z equals f of xy, and then if we have a level set, okay, then the gradient vector f will be perpendicular to the level set, right? So it means it's perpendicular to the tangent line, right? This is in R2, okay? But now in R3, then we have w equals capital F of x, y, z. Then for a level, we don't have a level curve. For the level set will be a surface, right? So it will be a surface. Okay, this is the surface, and we know the gradient of capital F is again perpendicular to the surface, the level set. Well, it means is also perpendicular to the tangent plane. Okay, so for the tangent vector, so for normal vector, so normal vector of the tangent plane, we can pick it to be, so we can pick it to be the gradient vector. Okay, so now we know a point on the tangent plane, that's the ABC, and now we also have a normal vector, that's the gradient, okay, which is fx, fy, and fz. So that's why we get this tangent plane equation. So far, so good, everybody. So I really hope you can keep in mind. Okay, are we in R2? Are we in R3? Okay, so let's look at this again. So here, z is a function of x and y. Okay, if we look at the graph of this function is a surface in R3. Okay, but okay, so let me write it down. So graph of z equals f of xy is a surface in R3, but the level set, okay, f of xy equals to a constant. So this is constant is curve in R2. Okay, now for now, w equals f of xyz is a three-dimensional hypersurface in R4. Okay, then the level surface, okay, so level surface, level sets, f of xyz equals to a constant. This guy is a surface in R3. Okay, so I really hope that think through it. Okay, try to understand it. Okay, the dimension, we have a lot of dimensions. Okay, so surface, if say the surface has dimension n, then the level curve or level set or level surface, okay, is one less dimension than the surface itself. Okay, now we have two formulas for the tangent plane. So let's look at the following example. Let's use formula 1, okay? Formula 1, what is formula 1? Formula is z equals f of ab plus fx. Evaluate ab, x minus a plus fy ab times y minus b. My comma is so ugly. Let me erase this. Okay, so let's see. Partial f partial x is so is derivative of x squared is 2x, so we have 2xy, and then there's no x in the 2y cube, so it's 0. Fy is derivative y is 1, so x squared plus 6y squared. Okay, then fx evaluates at, you can see this is just the point 1 1. Fy evaluates at 1 1. What is that? 2 times 1 times 1 is 2. Here 1 plus 6 is 7. So z equals, by the way, f of ab, f of 1 1 equals 1 plus 2 equals 3. That's why you see this 3 is actually f of 1 1. Okay? So z equals f of 1 1 is 3 plus partial f partial x, evaluate at 1 1, which is 2, x minus 1 plus 7 y minus 1. That is, let's distribute 2x minus 2, 7y minus 7. So 2x, 7y, 3 minus 2 is 1, 1 minus 7 is negative 6. So far, so good, everybody. So this is the tangent plane using the method we did before. Now, let's use the second method. So we consider this is a level surface of a three-variable function. Okay, so we define the three-variable function f x y z b left hand side minus right hand side. So z minus x squared y minus 2y cubed. And then fx is, okay, minus 2xy, right? That's it. Fy will be minus x squared 6y squared, right? Fz will be 1. So far, so good, everybody? Okay, then we plug in the point 113. So minus 2 times 1 times 1 is minus 2. We plug in 113. Minus 1 minus 6 is minus 7. And fz is constant 1, so no matter what number we plug in, it's still 1. Then ready, fx, so negative 2 times x minus x coordinate 1. And then we have minus 7, y minus 1, plus 1 times z minus 3. Okay, the point 3 here. So distribute minus 2x plus 2 minus 7y plus 7 plus z minus 3 is negative 2x minus 7y plus z. Let's move the constant on the other side. 2 plus 7, 9. 9 minus 3 is 6. But move the 6 to the other side, become negative 6. And you can see they are actually the same, right? If we move the 2x and 7y on the left, it becomes negative. Then we have the same equation. Okay, so right now we know 2 methods to find the tangent plane. So you can use whichever way you want. Okay, let's continue. So find the tangent plane of the surface at the point 0, 1, negative 2. Okay. So we would say the second method is more general because sometimes maybe it's hard to solve z in terms of x and y. Okay, now f of x, y, z, you always use the left hand side minus the right hand side. So we have sine of x, y, y to the 4 minus 7 ln of y plus 3z squared minus 5y minus 7. So far, so good, everybody? Okay, now calculate. Partial f, partial x. So x is the variable, y and z are constant. Derivative of sine is cosine xy. Then chain rule, xy prime. Derivative of x is 1, so constant multiple y stay there. And there is y to the 4, right? And then all the rest, it has no x in it, so the derivative is 0. So let's combine them. We have cosine xy times y to the 5th. Right, how about fy? Ooh, fy, we take the derivative with respect to y. Ooh, we need product rule because this guy has y, this guy has y. Product rule, so sine xy prime, y to the 4 plus sine xy. Derivative of y to the 4 is 4y cubed. And then 7 ln y, derivative is 7 over y. 3z squared gone. Negative 5y derivative is negative 5, right? Okay, derivative of sine is cosine xy. But the derivative of xy is, because we're taking the derivative with respect to y, it will be x. So copy down. So far, so good, everybody? Alright, let's continue. Fz is, first term is gone. 7 ln of y is gone. Oh, 3z squared becomes 6z. And that's it, right? Oh, my 6 is ugly. Okay, now let's plug in the point 0, 1, -2. Let's see. Cosine 0 is 1. Y to the 5th, 1 to the 5th is 1. So this is 1. And then Fy evaluated at 0, 1, -2 is cosine. Oh, because of this x, when we multiply by 0, is gone. Sine of 0 is gone. Y is 1, so -7 minus 5, -12, right? And then Fz evaluate at 0, 1, -2. 6 times -2 is -12. So we have fx1, x minus 0, minus 12, y minus 1, minus 12, z minus -2, so y plus 2, z plus 2, sorry. So we have x minus 12y plus 12 minus 12z minus 24. So x minus 12y minus 12z. Okay, 12 minus 24 is -12, but when we move -12 on the other side, it becomes positive 12. So this is our tangent plane equation. Do you have the same answer? All right. How about, so you see what we have learned in this session, we can all extend to a function with 3 variables. Okay, we can talk about the linear approximations. Then now change of f is the gradient times the run vector, but now the one vector has 3 coordinates, change in x, change in y, and change in z. Okay, so similar, the same ideas as before. We just extend one more dimension. And gradient vector field. So before the gradient of f is this gradient field is on the xy plane. Okay, so this is before, but now our gradient is a vector in the space. Okay, so our gradient field is a 3-dimensional vector field. Okay, and graphing gradients in space is usually hard to do by hand because we would need to plot a lot of vectors in space. Okay, sometimes it's hard to tell where it's located. So computers are better at this, but even then, it may be hard to make a printout look good. Okay, so can you see this? All right. So in the GeoGebra, later on I will show you how to draw a vector field, okay, in the GeoGebra software. We also have a extra credit project for that. Okay, so let's look at the properties of the gradients. Okay, now we have 3 variables x, y, z. Assume that the gradient is not 0. Then the gradient also points in the direction of the maximum rate of increase of f. The negative gradient points to the direction of maximum rate of decrease of f. Okay, the magnitude of the gradient is maximal directional derivative of f at the point. And the magnitude of the gradient is larger where the level surface of f are closer together, because it means if the level surface are closer, it means the slope is large. And we know slope is like the directional derivative is kind of proportional to the length of the gradient vector. Okay, the directional derivative of f is 0 in the direction perpendicular to the gradient vector. And the gradient vector is normal to the level surface of f that passes through the points. Yeah, so same thing holds as we learned before. Okay, let's continue. So for a function of the form, a level set is Yeah, it's a surface. Can you see that? So if a point lies on this level surface, f of x, y, z equals k. Let's say k is a constant. Then the gradient is normal to the surface at the point. So that's why we can use the gradient vector as the normal vector of the tangent plane. Okay, so we can use the gradient as the normal vector of the tangent plane. Okay, of the level surface. Okay, let's look at the following example. Consider the function f equals x squared plus y squared. And because we have no z there, we know this is a cylinder. This is actually a circular cylinder. Because when we use a plane, z equals to a constant, intersect the surface, we'll get a circle. Right? And the diagram on the left shows some level surface for f. On the right, we see the gradient as well. Okay, part A, compute the gradient. Okay, that's the derivative with respect to x, which is 2x. Then the derivative with respect to y, which is 2y. There's no z. The derivative with respect to z is 0. Suppose we start at the point 1, 2, 3, and we need to move to a new point Q that is at a distance 1 over 100 units from the point P. What would Q be if we want the function to increase as much as possible? Okay, specify all 3 coordinates of the point Q. You do not need to simplify each number. Okay, what does that mean? Okay, so suppose we're at P, right? We want to move to a point Q such that at a distance. Okay, so we know the distance of PQ equals 1 over 100, right? And the point P is 1, 2, 3. Okay, what would Q be if we want f to increase as much as possible? Well, increase as much as possible, it means the gradient of f should be in the same direction as the PQ. Right, everybody? Okay, so how can we find PQ? We know a vector. How to fix a vector? We need a length and we need a direction. We already know the length 1 over 100, right? How about direction? Well, it's in the same direction as the gradient vector, but that we don't want a magnitude, so we want to have a unit vector to denote the direction. So we use the gradient vector and divide it by its length. Then we get a unit vector just to denote, to point out the direction of it. Okay, so now after we find PQ, then Q is just P, the point P, plus PQ, the vector PQ. So far, so good, everybody? Yeah, why is that? See, this is OP, right? O is the origin, P is right here, Q is right here. So OP is the same as the point P. Okay, when we plus PQ, then we get OQ. So OQ is the same as Q, the point Q. Okay? Alright, so let's do it. What is the length of this gradient vector? What is the gradient vector at that point? Okay, so gradient vector at P. Let's see. We have 1, 2, 3, so 2 times 1, 2 times y is 2, and there's no z, right? So 2, 4, 0. And what is the magnitude of it? 2 square, 4 square, and 0 square. 2 square is 4, 4 square is 16. Square root of 20 is the same as 2 root 5. Then what is the unit? I write too large. Okay. Let me try to write smaller here. So then the unit vector is gonna be 2, 4, 0 over 2 root 5. You can see I can get rid of the 2. Then we have 1 over root 5, 2 over root 5, and 0. Okay, so PQ is 1 over 100 times that. Then the Q is PP is 1, 2, 3 plus PQ. PQ is 100 times this vector. So that is 1 plus 1 over 100 and root 5. 2 plus 2 over that. Oh, that's the same as 1 over 50 root 5. And 3 plus 0, so it's 3. So this is the point Q. Is that okay, everybody? So sometimes it's good to draw a picture and then you can understand the relationship between the points and the vectors, and then maybe the gradient, etc. Okay? Alright, let's continue. So don't forget, this session is quite long. If you have some questions, please print screen and then you can ask me either in class or office hours or send me an email. Next, consider the function. This is a function. The diagram shows some level surface for F and the gradient field as well. Compute the gradient field. Okay, so what's the gradient? Partial F partial X. Derivative of X squared is 2X. No X anymore. Derivative of Y, derivative with respect to Y is 4Y. Derivative with respect to Z is 6Z. Okay, that is part A. Kind of easy, right? How about part B? Find the tangent plane. Okay, of the level surface f of xyz equals 6. Okay, so then we know the normal vector is, so the normal vector will be the gradient. Sometimes the gradient I remember to draw an arrow, sometimes I forgot. Yes. Okay, but if you can remember, and try to write down the arrow on top of it. Okay, so evaluate at the points -1, 1, and -1. Then we have -2, 4, -6. Right? And then we're ready. We have the normal vector. We have a point on the plane. So the plane equation is -2. X minus -1 is the same as x plus 1 plus 4. Y minus 1 minus 6. Z minus -1 is the same as z plus 1. -2x minus 2 times 1, -2. 4y, 4 times 1, 4. 6z minus 6. So let's group the variables on the left hand side and move the constant to the right. 2, 4, 6, 12. -12 move to the other side, become 12. Oh, can you see every term has a factor of 2? We can simplify it. And sometimes people would like to make the coefficient of x is positive. So let's divide it by -2. Then we have x minus 2y plus 3z divided by -2 to the 12 become -6. So far, so good, everybody. So this is the tangent plane. Okay, so Yeah, this is a tangent plane at the points -1, 1, and -1. So far, so good, everybody. If you want to draw what is this plane look like, you can always use our GeoGebra Hangout. Let's see. Let me find it here. Our GeoGebra projects, actually, we use the information z equals a function of x, y, but we can do the similar things here. We can change the function to type in this function, okay? And then we can also find the gradient vectors, okay? So this is our GeoGebra project. I will assign it when we visit chapter 14. But I want to show you here for a function with 3 variables, even though we cannot draw it in the space, but you can actually calculate its derivative. Okay, partial f, partial x, partial f, partial y, and partial f, partial z. Then you can use this information and together, similar to what we have here, to find the normal vector. Once you have the normal vector, then you can find a tangent plane to it. Okay, if you have time, please come to my office hours. I'm very happy to show you how to find the tangent plane or for a surface, okay, like this in general. All right, let's continue. Last example of this session. I know this session is quite long, right? Okay, so this is the last example of this session. Find the tangent plane to the following surface at the point 2, 0, 1. Okay, so similar to what we have done before. So first we define the surface. We use the left hand side. Minus the right hand side. Okay, so that's the surface, and then we find the gradient, partial f, partial x. Take the derivative with respect to x, give us z. X squared give us 2x, so 6xy. And then the remaining 2 terms has no x. Okay, how about the derivative with respect to y? The first term has no y. Second term, we get 3x squared. Oh, and then this is chain rule. yz prime is z. Okay, and then take the derivative with respect to z is x. Second term has no z, so it's gone. Then chain rule, but yz prime, we take the derivative with respect to z is y. So far, so good. And now we plug in 2, 0, 1. Z is 1. Y is 0, so 6xy is 0. 2 squares 4. E to the 0 is 1. Z is 1. X is 2. Oh, this guy times y is 0. So 12 minus 1 is 11. 2 minus 0 is 2. Okay, so we get the normal vector. And what is the point? 201. You're ready. So 1x minus 2, 11, y minus 0, 2, z minus 1 equals 0. X minus 2, 11y, 2z minus 2. So we have x, 11y, 2z. -2, -2 is -4. Move to the other side, become 4. So this is our tangent plane. So far, so good, everybody. We mark. Here, you can also define your f to be just your left-hand side because your right-hand side is a constant. Okay, so So if in this case, if you just defined f of x, y, z is the left hand side, then your level set is just f of x, y, z equals 1. It's still a level set. But if you defined f of x, y, z be the left hand side minus the right hand side, then our surface corresponds to the level set of f of x, y, z equals 0. And this in general is better because, for example, if you have xz plus 3x squared y equals e to the yz plus 1, then you cannot just let f of xy to be your left hand side because that is not equal to a constant. Okay, so we want to define our f such that our f equals to a constant is a level surface that corresponds to that surface. Okay, so in order to not get make you confused, just erase this. So from now on, just remember when you define f, that is the left hand side minus right hand side to avoid mistakes. Okay. But if some of you if you really understand this, then you know that we're not necessary to let f be the left hand side minus right hand side. Sometimes it could be just the left hand side if the right hand side is a constant. So far so good, everybody. Okay, yeah, so this guy corresponds to the levels set of, okay, so in general we denote this is the left hand side minus the right hand side. Okay. Alright, so that is it for session 12.7. I want to talk about 12.7 first and the 12.6 because I want to introduce the gradient first. Then we can use the gradient to define the directional derivatives. Okay, so have a nice day. Bye.